किती विद्यार्थी आहेत? मला वाटतं फक्त 10च आहेत. Okay, doesn't matter. So we'll first revise what we have done yesterday. And so can somebody confirm that I am audible and the board is visible? Somebody from online?
Yes, sir.
Okay, thank you. So yesterday we have discussed about the Morse test, wherein what we did was we were supposed to find out the frictional power of the engine. And for that, what we had done was, alternatively, we went for cutting the supply of the spark from ignition system. That is, where the spark plugs were not fired alternatively, and correspondingly, we have found out what is the brake power of the engine. So initially, we have found what is the brake power when all the engines are fired. Okay, so this was your brake power corresponding to when all the engines were fired. Then we had power corresponding to first cylinder was not fired. So here we have written IP is equal to 0. Then second, when the second cylinder is not fired, and the third case, when the third cylinder is not fired. Okay, so correspondingly, we had 4 brake powers, one corresponding to when all the engines are fired, when the first cylinder is cut off, second cylinder is cut off, and third cylinder is cut off. And what we did finally was one, this equation we called it as 1, and we said that 1 minus 2 gave us I1. 1 minus 3 gave us I2. And 1 minus 4 gave us I3. But we said that I1 plus I2 plus I3 is equal to I. And now we know what is I, we know what is B. That is total brake power we are having, total indicator of the power of the engine we are having, and I minus B we found out was equal to the frictional power of the engine. So this is how we are supposed to find out the frictional power of the engine. Now, here what is the concept basically? So the concept here is that, so basically, initially we will be running this test, first test. That is when all the engines are running, all the cylinders are working, all the spark plugs are firing, we will have a brake power. Now, this suppose we take this particular test at 2000 RPM, suppose 2000 RPM. Now, if F1 minus F1, if it is supposed to be cancel out, this is F1. So if F1 minus F1 cancel, if you want to cancel out, then we have to ensure that here also the engine is running at 2000 RPM, here is also running at 2000 RPM, here also it is running at 2000 RPM, here also it is running at 2000 RPM. How? Because here see, indicated power is 0, but obviously the frictional power is there. And when the frictional power will get cancelled out, when the frictional power here and here is equal. And when it is going to be equal, when the number of rotations per I hope I'm audible. Am I audible? Am I audible? Yes, sir. Can somebody confirm? Okay. So what we did was conduct all this particular tests at the same speed. So generally, when we take the go for experimentation, what happens is हे टेस्ट करताना आपल्याला तिन्ही सिलेंडर मध्ये पॉवर तयार होते. त्यामुळं पॉवरची जी काही व्हॅल्यू असेल ऑब्विसली ही जास्त असेल. हे जास्त असल्यामुळे काय होतंय इंजिनचं स्पीड जास्त राहते. परंतु इथे ज्या वेळेला येतो आणि आपण एक सिलेंडर कट करतो त्यावेळेला या सिलेंडर मधून एका सिलेंडर मधून येणारे पॉवर कमी झाली. आता 2 सिलेंडर मधून फक्त पॉवर मिळते. ऑब्विसली द अमाउंट ऑफ पॉवर रिसीव्ड बाय द क्रॅन्कशाफ्ट इज गोइंग टू बी लेसर and there is a tendency that speed will come down. So what we have to do is now we have to go for acceleration. We have to press the accelerator and bring the speed back to 2000 before we take the reading, this reading. Okay, so every time we have to ensure that this particular speed of 2000 is being maintained irrespective of whichever cylinder is cut, because we want the frictional power to remain same. इथं आणि इथं हे दोन्ही मध्ये ज्यावेळेला आपण F1 मायनस F1 करायचं असेल तर ही F1 ह्यातनं मायनस करून इथं 0 पाहिजे असेल तर ही F1 आणि ही F1 सेम पाहिजे. ते कधी असं असू शकेल ज्या वेळेला ही F1 आणि ही F1 सेम येईल. ती कधी येईल ज्या वेळेला ही F1, व्हॉट इज दिस F1? फ्रिक्शनल पॉवर करस्पॉन्डिंग टू द फ्रिक्शन बिटवीन द पिस्टन अँड द सिलेंडर. मग स्पीड चेंज झालं की नंबर ऑफ फ्रिक्शन्स विल बी चेंजिंग. म्हणून आपल्याला स्पीड कॉन्स्टंट ठेवावं लागतं. सो रिमेंबर दॅट दिस पर्टिक्युलर टेस्ट हॅज टू बी टेकन विथ अ कॉन्स्टंट स्पीड. And finally, we will find out I1 plus I2 plus I3 is equal to I, and we have now B. So this I minus this particular B, that will give you F. So I minus B is equal to F. So this value minus this value will give you the final frictional power of the engine. So hope everybody understood how we are calculating the frictional power, and let us move on to our today's experiment, that is the heat balance sheet. Now, what is heat balance sheet? So in order to understand the heat balance sheet, actually we have learned this particular heat balance sheet in theory classes. So basically we know, we have heard the word balance sheet. Where we have heard the balance sheet word? In accounts. In accounts. What it indicates? It indicates that on one side we plot where the money is coming from, and on the other side we put where the money is going, and we finally say that the amount credited is equal to amount debited. Okay, so that is what we call as a balance sheet, accounts balance sheet. Here we are talking of energy balance sheet. Energy balance sheet. So where the energy is coming from and where the energy is going, that we will be balancing. Okay, so basically where the energy is coming from? So energy is coming from the fuel. Energy is coming in the engine in the form of fuel. So we have energy MF into CV. Okay, this much kilowatts. So this will be, sorry, MF into CV. This will be this much kilowatt of energy. Let we say this is 100%, because there is no other source of energy coming for the engine. So here we will write how much percentage this is. Okay, so let this be X kilowatt. X kilowatt. Okay, so how we will find out that energy coming? MF, we have mass of the fuel consumed by the engine multiplied by calorific value of the engine. Okay, so that will give you how much energy is being input to the system. So input energy to the system. On this side, we are going to plot where the energy is going. So we know that our basic aim for construction of engine is to convert the energy, fuel energy, chemical energy in the fuel into power. So the most important conversion will be happening in terms of brake power. So corresponding to energy corresponding to brake power. Energy corresponding to brake power. Okay, so let this will be Y kilowatt. Y kilowatt. Okay, so let this be around 30%. Just I am approximately writing this percentage. Okay, approximately writing this particular percentage over here. So let that be Y kilowatt. So out of the X amount of energy, whatever we have received in the engine, Y amount of energy which corresponds to almost around 30%, is being converted into power. Now, how to find out this? How to find out this? We have the equation BP is equal to 2 pi NT upon 60,000 kilowatt. Okay, so this equation we will be using to find out this percentage. Okay, okay. So now out of the 100%, around 30% of the energy has been converted into power. Now, where the remaining energy goes? So some amount of energy goes to the cooling water. So some amount of energy goes to cooling water supplied to the engine. So we know that we have a cooling system in the engine, and we have the water coming into the engine, and it is cooling the different parts, and the water is going out, picking some heat. Okay, so let that be Z. So Z kilowatt of energy, suppose approximately, suppose it is 20%, or let's say it is 15%. Okay, 15% of energy is going to cooling water. So now the question arises, how to find this? So for that, what we have is, we have some indicators, temperature indicators on the engine. And what we need to know is, whatever the heat lost by the engine, whatever is the amount of heat lost by the engine, is the heat gained by the cooling water. We assume that whatever amount of heat lost by the cooling engine, that will be gained by the water which is circulated in the cooling system. So this Q, amount of heat loss, we can calculate it by mCp delta T. So what is M? M is the mass flow rate of water. Yeah, please. Anybody having any doubt? Cooling water, Q is so the heat carried away by the cooling water, Q is equal to M multiplied by Cp multiplied by delta T, where M is the mass flow rate of air, water. Cp is the specific heat of water, and delta T is the temperature difference between the inlet and outlet of the cooling water. So as the water moves through the cooling jackets, it picks up the heat, and the temperature increases from some A value to B value, or some particular value to a particular value, because as the water is being circulated in the cooling jackets, the temperature of the water goes on increasing. So the delta T indicates the amount of the temperature increase when the water is circulated in the cooling jacket. So mCp delta T will be can be calculated, and that will give you the amount of heat picked up by the cooling water or lost in the cooling water is equal to Z, and say it is approximately 15%. Say approximately, not necessarily. Okay, and next another source of loss is any other source of loss other than the cooling water? Anybody? Division B. Any other source? Yesterday, the morning itself, you have been taught. Can anybody unmute? Can anybody unmute and tell? Any other source where the heat is being lost? Yes. Anybody? I think you are able to speak. Okay. So what is can you suggest any other method by which we are going to use some energy? Anybody? Other than cooling water?
Exhaust gases.
Correct. Very good. So heat loss to the exhaust gases. Heat loss to the exhaust gases. Now, how to find out this? Suppose this accounts to A kilowatt. A kilowatt. Okay. So this particular A kilowatt, and it approximately again suppose around 10%. Suppose. Okay. So how to find out this A value? Can anybody? Can anybody? Okay, I will tell. So what we will be doing over here, we will be using one instrument, what we call as a exhaust gas calorimeter. Exhaust gas calorimeter. And what is this exhaust gas calorimeter? Exhaust gas calorimeter is nothing but a heat exchanger, wherein we assume that see how a heat exchanger is something like this. Suppose you have a heat exchanger like this. We are making the gases to flow in over here, gas flowing in here, the gases are flowing out over here. Okay, and we are supplying the cold water over here, and we are taking the hot water from here. So what we are assuming here is that, so here there will be a set of pipelines through which we are making the water to flow, and we are assuming that all the heat available in the exhaust gases is being transmitted to the water. And therefore, suppose this exhaust gas is coming from the engine when we allow to go into this particular heat exchanger. And when it flows out here, the gases will be at atmospheric conditions. Okay, which means, in other words, that all the heat in the gas above atmospheric condition. Obviously, whatever is coming out of the engine is at atmospheric conditions. So whatever the heat was there, now air was given to the engine at atmospheric condition. Then it was heated up by compression due to combustion, etc., etc. So whatever the extra heat was added to the charge, that is being taken out and it is given to the water over here. So heat lost by the gases is equal to heat gained by the water. On that particular assumption, we can calculate the amount of heat which is lost in the cooling water, the water used in the calorimeter. Again, Q is equal to mCp delta T, where m is the mass flow rate of the water going into the calorimeter, Cp is the specific heat, and delta T is the temperature difference between the inlet of the water to the calorimeter and exhaust of the water to the calorimeter. Okay, so from this particular equation, again we can find out the heat loss to the exhaust gases. Okay, and let this be A, which is around 10%. And then there are so many other losses, which like conduction losses, convection losses, and so many other losses, which we are unable to exactly find out. And we put them under unaccounted losses. Unaccounted losses. Okay, so this unaccounted losses, let this be P kilowatt, and which will be equal to, or we can say this B is equal to X minus Y plus Z plus A. Okay, that is equal to B. So that will be equal to 100 minus 30 plus this 40, 55. So 100 to 15. So 15 and 15, 30, 30 plus 30, 60, 100 minus 60, this is around 40%. Okay, now you can see this total becomes 50, 60 plus 40, 100, 100%. Okay, and here you will calculate this values, this X and this Y plus Z plus A plus B, that will be equal to again whatever X value, that will be same equal to X. So this is how we go for heat balance sheet. So what we are doing in the heat balance sheet, we are trying to balance out or find out where the energy is going, whatever we have given to the engine. So first we will find out where the energy is coming from. Energy is coming from the fuel. So the fuel energy is equal to MF into CV, which is the input to the engine. So by calculating the amount of fuel consumed by the engine, okay, and multiplying it by calorific value of the fuel, we can find out what is the amount of energy in the fuel which we have supplied to the engine. And then coming on this side, what we will be doing here, some part of that particular energy is being converted into work. So how to find out? We have BP is equal to 2 pi nt 60. This much kilowatts of energy is being converted into work. So some amount of X is being converted into power, which was Y kilowatt. Okay, that we have found out by using this particular formula. Now, some amount of heat is being lost to the cooling water. So Q is equal to mCp delta T. That will give you the amount of heat lost to the cooling water, where M is the mass flow rate of the cooling water, Cp is the specific heat, and delta T is the temperature difference between input to the water inlet to the cooling system and water outlet from the cooling system. So the temperature difference between that is this delta T. So knowing this particular delta T, you can find out Q. So what will be required here? This particular two temperature and this mass flow rate. Now coming to heat loss to the exhaust gases, how we can find out? Q is equal to mCp delta T again. So what is the assumption over here? The assumption is that whatever heat is there in the exhaust gases is completely transferred to the water, which is used to cool the calorimeter. So basically this particular calorimeter is a heat exchanger. Okay, and in this particular heat exchanger, what we are trying to do, whatever the heat is there in with the exhaust gases coming out of the engine is being transferred to the water, which is circulated into the calorimeter. So now Q is equal to mCp delta T, where M is the mass flow rate of the water flowing through the calorimeter, Cp is the specific heat, and delta T is the temperature difference between the inlet to the calorimeter and water inlet to the temperature of water inlet to the calorimeter and water outlet to the from calorimeter. So knowing this particular two temperature and the mass flow rate, you can find out what is the heat lost in the exhaust gases. Okay, and finally we have one term called as unaccounted losses. We are clubbing this everything together, which we are not counting under these three heads. Other than this three, whatever is there, we count under this unaccounted, and we say this unaccounted loss is equal to this 100% minus this plus this plus this, or whatever X value here minus Y plus Z plus A. So addition of the three when subtracted from X, that will give you the unaccounted losses over here. Okay, which will be again equal to when you add this and here, this number and this number will be again equal. Okay, in other words, it means this 100% if you consider, then this, if you calculate in terms of percentage, this percentage will become 100 and here 100. So we are balancing it. So that is where we call it as a balance sheet. So this is the energy balance found out for the engine. Okay, and we call it as heat balance sheet. Okay, so now let us go to the engine and we will try to find out what is the calorimeter. So let us see how the calorimeter is. So this can be done for all the engines. Okay, so you can see over here, this is a calorimeter where you can see here there are temperature sensors. Okay, here there are temperature sensors. There are temperature sensors. Now, what are these temperature sensors? So here, through this particular pipe, your gases are coming from the engine, which is going into the calorimeter. This is the pipe through which gases are flowing out from the calorimeter. So gases are coming in here, we are measuring the temperature. Gases are going out, we are measuring the temperature. Okay. Now, here, this is the water given to the calorimeter for cooling. So in this particular calorimeter, what happens? Whatever the heat is there in the gases, that will be transferred to the water, whatever we are giving for cooling. and the water will be circulated through the passages, cooling passages, and it will be taken out here. So outlet it is here. Okay, so water is inlet, here it is outlet, here it is outlet. Okay, so now here we measure the temperature of inlet water, and here you can see over here, here we have the temperature of outlet water. So by noting down this particular two temperatures, that is inlet water temperature and exhaust water temperature, we can find out and the mass flow rate. Now, in order to measure the mass flow rate, here we have here manometer over here. So in this particular manometer, you can see we can measure the mass flow rate of the water directly. So when we start the flow, here पानी चालू करता का जरा. हालत नाही तिकडनं चालू केलं का पाणी. Okay, so this is a manometer where here the float is there. This float will rise, and here there are some graduations. Marking is there, and corresponding to the flow of rate, as the flow rate increases, this float goes on increasing, lifting up, and correspondingly we can take the reading of what is the mass flow rate of water. So this particular mass flow rate here is indicated is for the cooling water given to the engine cooling, and this one is given for the calorimeter. Okay, so here we have two manometers for measuring the water flow rate of the water, given to one to the cooling system and another to the calorimeter. And when you come over here, now, yesterday when we have calculated the most test, the RPM reading we were taking over here, but this particular temperature reading we were not taking. So you can see over here, here it is written, T1 is the engine and calorimeter water inlet temperature. Inlet temperature of the water is T1. So if you put this particular knob at 1, that means it is T1. So that is the inlet water temperature of both engine and your calorimeter. Then T2 is the engine water outlet temperature. So if you now put this particular knob to second point, then it indicates water outlet temperature from the engine. Then correspondingly, T3 is the water outlet temperature from calorimeter. T4 is the exhaust gas temperature before the gases are being entering into the calorimeter, and T5 is the exhaust gases after while coming out of the calorimeter. So here T4 and T5 we are measuring in order to ensure that all the heat available. See here, this is the temperature of the gas going into the calorimeter, and T5 is the temperature of the gas coming out of the calorimeter. We want to ensure that T5 is almost equal to atmospheric conditions. And when this happens, we can assume that all the heat in the gas is being transferred to the water, and that will be appearing in the form of T3, that is the calorimeter water outlet temperature. Okay, so here by moving the knob from 1, 2, 3, 4, 5, we can get different temperatures. Okay, when the engine is started, we will be able to get different temperatures. Now, similarly, this was for multi-cylinder engine. Now, moving ahead, we can do this for yeah. So here also we have, here you can see for this particular, for this single cylinder diesel engine, we can also have the same test being done. So some amount of brake power will be converted into brake power, which we can find out using this rope brake dynamometer 2 pi nt upon 60, etc. Okay, where we'll be taking diameter of this pulley and the spring balance reading, etc. All these things, and we will be finding out the brake power. And when it comes to the temperatures, so you can see here by rotating this particular knob, well, now the engine is not started, and when we rotate this particular knob from 1, 2, 3, so you can see over here, T1 is the water inlet temperature to calorimeter, T2 is the water outlet temperature from calorimeter, T3 is the exhaust gas outlet from the engine, T4 is the exhaust gas inlet to the calorimeter, T5 is the exhaust gas outlet from calorimeter, T6 is the water inlet temperature to engine, T7 is the water outlet from engine, and T8 is the ambient or room temperature. And correspondingly, so the different temperature we are measuring over here. And similarly, here we have a manometer to measure the water flow. Okay, so when we start the water flow here, the water पाणी चालू केलं नाही अजून त्यामुळे ते होत नाही. So here the this particular will be lifted up, and you can see here it is lifted. Yeah. So here this was the arrangement for measuring the fuel. Okay. So here we have one marking and here we have another marking. From here to here it is 50 ml. So we will allow the fuel to start from here. We will start a stopwatch and let the fuel come over here at this marking, which accounts for 50 ml. And we will counter what is the okay. So I hope everybody has understood how we are calculating the heat balance sheet. So basically what we are doing here is we will be trying to balance or compare the amount of energy given to the engine and amount of energy which is lost in different forms. Okay. So on one side, we will be writing where the energy is coming from, which we have already I have already shown you. We will be writing it in the form of where the energy is coming from. It is coming from the fuel. So here you can see the energy is coming from the fuel that we have written it in the form of MF into CV, which accounts to some number. We say this is 100%, and some part of that energy is being converted into brake power, which we are calculated using 2 pi and upon 60,000. Okay, which is we are saying it is Y kilowatts. Then some amount of energy is going to cooling water. We are calculating using the formula Q is equal to MCP delta T, which accounts for around Z kilowatts. And some amount of energy is lost to the exhaust gases. Again, we are finding out using the formula Q is equal to MCP delta T. So this was the so that is where I just shown you two manometers. One manometer corresponding to measurement of mass flow rate of cooling water to the cooling system, and another manometer for measuring the mass flow rate of the cooling to the exhaust gas calorimeter. And we have different temperature sensors. So here we will be using the inlet temperature difference of inlet water to the engine cooling system and outlet water from the cooling system. Here we will be using the temperatures inlet to the calorimeter, water inlet to the temperature of water inlet to calorimeter, and temperature of water outlet coming from the calorimeter. So that temperature difference we will be using over here. And finally, we have the unaccounted losses. Unaccounted losses is equal to here X, which is B, which is equal to X. That is the energy in the fuel minus energy that is converted into brake power minus energy lost in the cooling water, minus energy lost in the exhaust gases. That will be your B. Okay, and that accounts to almost to, suppose here if this we consider this as 30%, 15%, 15%, then this will become 40%. If these numbers are higher or this number is higher, then this will be going on decreasing. So here this is the area where we have to concentrate, because we have to decrease this particular number, we have to decrease this particular number, we have to decrease this particular number, and we want to increase this particular number. Okay, so in order to find out where the energy is going, so that we can, in order to increase the efficiency of the engine. So what is thermal efficiency? Thermal efficiency is this Y divided by X. Y is the energy output, which is converted into brake power. And what is this? It is the energy coming in the form of fuel. So Y divided by X is your thermal efficiency, which accounts to around 30%. Okay. So we want to increase this. So we want to increase this. And in order to increase this, all this terms has to be reduced. So we want to reduce the amount lost to the cooling water. So we use different materials. We want to reduce the heat loss to the gases. So we divide the system in such a manner that we have minimum losses of the heat going into the exhaust. Preferably we use turbocharger, etc. That this losses can be reduced because amount of energy which is lost over here can be recaptured in the form of supercharger or turbocharger. Okay, so that was about the heat balance sheet. Anybody having any doubt with respect to heat balance sheet? Please let me know.
No, sir.
Okay, so basically this is what we do. And now let us, today I will show you the computerized engine what we are having. Okay, so that I will show you and I will explain the computerized engines. So here we have computer controlled, computer based VCR multi-fuel engine test rig. So this is your test rig what we are having in our lab, where this is our engine, which is again a single cylinder engine. Okay, and if you can see over here where I'm touching now, this is your injector. And presently, this particular, since it is an injector, which means it is running in presently in the CI mode. So you can see over here, this is your inlet system. Now the fuel is coming from the diesel tank. Okay, so from this particular diesel tank, the fuel is coming. Okay, it is coming like this. Okay, and we have another system over here. So this is another system which we can connect to another tank where we have here the petrol tank. Okay, so we can have this particular engine running on both the fuels, and that is where we call this as a multi-fuel engine. And when this is running in a multi-fuel engine, we will replace this particular injector by a spark plug over here, and we will give this from this particular ignition system, we will give the electricity supply, high voltage electric supplies to the spark plug, and we will give the fuel inlet, mixture fuel inlet mixture fuel to this particular carburetor. It will be supplied to the engine. Okay, and one more arrangement what we have here is this arrangement where you can see we have this particular so here when we rotate this particular engine, you can see the compression ratio. So the compression ratio is presently here. This particular line indicates it is around 13. Okay, now you can see that is changing. So what we are trying to do is we are moving the head towards the block or away. So by rotating this particular wheel, we are able to change the compression ratio in the engine. So preferably this is a engine which we generally can be used for testing different types of fuels. Okay, and when we run this particular engine, we are going to get all this particular data. So this is an airflow rate indicator. This is a fuel rate indicator. This is a torque indicator, torque produced by the engine. This is a temperature indicator. So you can see the channel 1, channel 2, channel 3, channel 4, like that it is going. So different temperature indicators are there. So you can see channel 6. So 1 to 6, we have 6 temperature. Yeah, so this was the temperature indicator. Then we have the speed indicator where we can read the RPM. And this is the temperature indicator, again, another temperature indicator. So we have different temperature indicators. The flow indicator, the fuel flow, we can read over here. Okay, and water flow over here. So two flow indicators are there. Temperature indicators are there. Speed indicator means where we can measure the speed of the engine, and this particular same thing, we have this particular on a so I have not started now. So this runs on a software over here. So basically, okay. So basically, in this particular engine, you can see this is the engine, what you are seeing, and whatever the engine when running, you can read the parameters over here, and simultaneously, this whatever the data, whatever you are getting over here, that will be going to that particular software, and the software will be plotting the different graphs, performance curves. Okay, speed versus load, performance versus load, all these particular graphs can be loaded over there. It can be clearly seen, or the PV diagram, the TS diagram. So all these diagrams can be seen over in this particular software. So this is a computerized multi-fuel variable compression ratio type of engine, where there is a provision for changing the fuel. So we can run it in the petrol mode or in the diesel mode. Both the mode we can run. During the diesel mode, this here it will be a injector. In the petrol mode, this will be a spark plug. Here there is a provision for changing the compression ratio. Okay, and when in a petrol mode, this is your ignition system. In the diesel mode, this ignition system will not be used. Here you can see now the fuel is coming from over here, and that is given to this injector. So during SI mode, this injector we will remove, and we'll put the spark plug over here, and we will give the spark connection with the help of this particular ignition system. So that is about the multi-fuel variable compression ratio type computerized engine. Okay, and here we have another engine, which is a computer controlled engine, where here you can see this is a computer controlled engine. Again, a single cylinder engine with a hydraulic dynamometer. There it was an eddy current dynamometer earlier. This is a hydraulic dynamometer. Water supply is given to this hydraulic dynamometer, and different sensors are there. You can see the different cables, and all these particular cables are connected over here to this particular system. And with this particular system, what you will do is you will be continuously monitoring the speed of the engine, or you want to change the speed of the engine, you can change setting on the computer, or you can change the speed of the engine. You want to change the speed of the engine through a computer. You can give the signal to the engine that you want to change the speed. So this becomes computer controlled single cylinder diesel engine, while this one was computerized. Here we cannot give the input from here. Manually we are changing the speed over here. So this is your accelerator. Okay, this is your accelerator, and in order to change the load, we have this particular torque meter. So by rotating this particular torque meter, we will change the load. So changing the speed and load is a manual in this particular case, and that will be reflected over here. And you can see the data when logged into the engine. The computer shows this particular data in this particular format. So you can see when the engine is started, here the torque value will come, fuel rate value will come, whatever the values here presently it is 0, so it will be here 0. So when the engine is running, here the data will become automatically logged, and when we click on the graphs, okay, here the graphs will be drawn. Okay, performance graphs. So here the graphs will be drawn. Presently, we don't have the engine started, and therefore the values are 0 over here. So when the engine will start, we will have a values over here, and we will get so that was how the engine, which was computer controlled one and computerized one. Okay, two engines were running. So today what we learned was how to find out the heat balance sheet of an engine, and then we saw the multi-fuel variable compression ratio type of engine, which is computerized one, and another engine which was the computer controlled, which where there is a provision for changing the speed and the load through using the computer. Okay, so we have a computer controlled engine, we have a computerized variable compression ratio multi-fuel type of engine, and obviously we have a single cylinder diesel engine on which we calculated the heat balance sheet. If you have any doubt, please ask, else we'll stop over here. Anybody having any doubt? Okay. So, people member saying no doubt. Okay, then if you don't have any doubt, please mark your attendance in the chat box and you may leave. So with this, we have completed all the experiments. Okay, we have conducted the load test initially. That is load test and speed test. Then we have conducted the yesterday the MOS test, and today we have the heat balance sheet. Also, we have seen all this particular test can be again conducted on the computerized engine, where we did not take any reading. Automatically, the reading will be the data will be taken by the computer, which is again displayed on the display, which we have seen now, and automatically it will plot the different graphs. Okay, so that was about the different practicals what we have in IC engine. So if you understood everything, please mark your attendance in the chat box and you may leave.